The Space Transportation System, America's hope for routine access to space. But before the hope can become a reality, the system must complete the 2 remaining missions of its flight test program, proving itself a reusable, reliable transport into space. Many of the flight test objectives have already been accomplished. A spectacular first launch, then successful second launch of the same spacecraft, 2 pinpoint landings, dramatic decreases in vehicle turnaround time, successful on-orbit checkout of the remote manipulator system, and solid evidence Columbia can be used as a scientific platform for Earth observation. The 3rd flight will push the system even further, proving Columbia can also be used for space observation, completing extensive tests of the remote manipulator system, checking out equipment to be used on later flights for medical research and drug manufacturing, testing an unpainted external fuel tank, which costs and weighs less than the 2 previous tanks, and planning the mission to last 7 full days, so that extensive thermal soak tests can be done on the vehicle and its systems. STS-3 is the most challenging and ambitious mission of the flight test program so far. Much needs to be accomplished for it to be a success, and for the Orbital Flight Test Program to reach its ultimate goal, routine space flights. The goal of STS-3 is to bring the system 1 step closer to that reality. Less than 1 week before liftoff, heavy rains at Edwards Air Force Base in California flooded Rogers Dry Lake Bed, making a landing there impossible. It was decided to land the orbiter instead at Northrop Strip, the alternate landing site at White Sands, New Mexico. Northrop Strip is located in the northern part of White Sands National Monument, in the middle of the U.S. Army's White Sands Missile Range. The remoteness of the area, a dry season that alternates with California's rainy season, and the availability of the Army's aircraft tracking network all contributed to NASA's decision to name Northrop Strip as an alternate landing site several years ago. A microwave landing system used by the orbiter during automatically controlled phases of approach and landing was installed on 1 runway. And a stiff-leg derrick was erected for hoisting Columbia atop the 747 aircraft, which would ferry it back to Florida. But the equipment necessary to safe Columbia after landing and prepare it for its trip back to the Cape was still at Edwards Air Force Base, over 1,000 miles from White Sands. And liftoff was only 4 days away. A highly organized, pre-planned operation was set in motion by NASA and implemented by the Department of Defense to move the tons of equipment and supplies from California to New Mexico. 2 trains were chartered from the Santa Fe Railroad for the journey. The cargo reached El Paso, Texas near sunset the 2nd day. There, the Southern Pacific Railroad took over. When the trains reached Holloman Air Force Base, they were unloaded, and the mobile equipment was driven the remaining 23 miles. The non-mobile cargo was transported by trucks. In concert with this operation, a plan to erect temporary facilities on the remote lake bed for support personnel, news media, and the public was also set in motion. A mobility unit from Holloman Air Force Base was called in to build shelters, barracks, a viewing area 5 miles from the landing site for the public, and a press area for the news media. Within 3 days, all construction was complete. Northrop Strip, which before consisted of only a runway and control tower, was now a total encampment, ready to safe Columbia after landing and prepare it for its trip back to Florida. This task could never have been completed without support from both the Army and Air Force. With their help, Northrop Strip was now ready to support the landing.
T-minus 15. The sequencer on the orbiter is now controlling the final seconds. 10. We are go for main engine ignition. 8, 7, 6. We have main engine ignition.
Roger, Columbia rolling.
Going to the blue skies.
Roger, sounds good. Columbia, Houston, you're go at throttle up.
Roger, go throttle up. We're going here too.
Columbia, Houston, negative seats.
Negative seats. PC-50, Houston.
PC-50.
Okay, there's 103. Boy, the first part of this ride is a real barn burner.
The crew for STS-3, Commander Jack Lousma, a Marine colonel and veteran of the Skylab 3 mission that stayed in space 59 days. The pilot, Air Force Colonel Gordon Fullerton. This was his first time in space. Fullerton was given primary responsibility for the extensive remote manipulator system tests done on this flight. With him at the controls, the arm demonstrated its payload handling capability.
Okay, well, we got a capture and a grapple.
Hey, that's good news.
Rigidized and got all the normal talkback.
That's super, and we're seeing the data.
The induced environment contamination monitor was to be unberthed first on this flight. However, the arm's wrist camera malfunctioned, making viewing the contamination monitor very difficult. Since the plasma diagnostic package was also to be unberthed, and because its guideposts could easily be seen with the aid of binoculars, it was substituted for the contamination monitor, proving again the flexibility of the system. The clearance between the plasma diagnostics package and the other experiments on the pallet was only 2 inches, a tight fit, but one which Fullerton was able to master within 5 minutes. 7 auto trajectories, computer-controlled maneuvers of the arm on an invisible plot were evaluated on STS-3 using the plasma diagnostics package. At the same time, the experiment also measured changes in the plasma field in and around the payload bay as Columbia traveled through the ionosphere, and monitored electromagnetic interference between the ionosphere and electronic equipment on board shuttle. The new knowledge will help scientists understand how larger celestial bodies move through plasmas and aid engineers in designing sensing equipment for future shuttle experiments. Several times during the mission, the arm and plasma diagnostic package operated in conjunction with a fast pulse electron generator to study the interaction of a stream of electrons emitted into the ionosphere. The result? A glow caused by atoms in the plasma being disturbed by the electron stream. Hopefully, this new knowledge will lead to a better understanding of how the same phenomena might occur in nature, for instance, in the aurora borealis. Other experiments studied the electrical buildup on the orbiter as it moved through the ionosphere, and contamination in and around the payload bay created by outgassings and thruster firings. These phenomena could affect scientific instruments and sensitive astronomy observations on future shuttle flights. On board, research in life sciences involved several instruments which were stored on the middeck. The plant lignification and weightlessness experiment was a preliminary study of lignin growth in zero gravity. It is hoped that in the absence of gravity, woody plants might produce less lignin, an indigestible skeletal substance which provides upward growth, and instead produce digestible nutrients, such as proteins and carbohydrates. A study of insects in flight was also done on STS-3. Commander Lousma prepared to examine the effects of weightlessness on some bees, moths, and flies, while on the ground, the principal investigator, high school student Todd Nelson from Rose Creek, Minnesota, did the same. Todd, who designed and developed the experiment himself, was one of 10 finalists in the National Space Shuttle Student Involvement Project, a joint venture of NASA and the National Science Teachers Association. His experiment flew on STS-3. The other finalists' experiments will fly on later flights. The purpose of Todd's study was to compare the natural flight characteristics of 3 species with their behavior in zero gravity. The insects were chosen primarily because of their different wing sizes. Todd wanted to find out if that factor would affect their flight behavior in zero gravity. After recording his findings in the Earth's gravity, he watched the crew's report from space.
Okay, hello there, space fans. Here we are in the good ship Columbia, speeding over the United States at 150 miles. Flying pretty fast, about 5 miles per second, but there are some among us who are actually flying faster than we are. And in this box, they're not only flying along with us, but they are flying themselves. So they're actually going a lot faster than we, I think. Most of them have positioned themselves around the periphery of the box or fastened themselves onto something. And unless we agitate them a little bit and make them get going, now it seems like the moths are doing a little better than the bees. The bees are just sort of tumbling around without flapping their wings. But the moths, every once in a while, you can see that one flying right there. He seems to have adapted to some degree to zero gravity. And there are a few bees like this one here. He's just floating around. He's taking the easy way out like Gordo is now. You don't see Gordo flapping his wings in zero G.
Todd gathered much data from his experiment, and with the aid of his sponsor, the Avionics Division of Honeywell Incorporated, will report the findings in a paper to the National Science Teachers Association. The Electrophoresis experiment verification test checked out the prototype of a more elaborate manufacturing device, which will be flown later on. The device separated chemical agents in fluids.
Hey, ladies and gentlemen, good evening and good afternoon, space fans. I'd like to tell you what we're doing here in the Space Shuttle Columbia. We're speeding over the world at about 17,500 miles per hour, now over the United States. And we're doing some medical experiments, among other things. This one I have right here is called an Electrophoresis experiment. It simply is a electrical way to separate out various chemical agents that cannot be separated out very easily on the ground. And it's a very expensive process. However, in zero G, these chemical agents can be separated out. and used for various pharmaceutical and other medical purposes. But basically what we have here is a tube in process. It's inside of this container. The tube is just like this and has a fluid inside, which is actually a carrier for the agent which is being separated out. We have a sample that we use to place right in this slot in here, and the sample is contained in a freezer. Inside of this freezer are several small samples which are used in this electrophoresis experiment. And then once the experiment is processed and the various chemical agents are allowed to move along this tube and are separated out, when the process is completed in about an hour, then the whole sample is frozen and it is then taken and placed back in this cryo freezer for analysis back on the ground. But this is the forerunner of a pharmaceutical experiment, and I think that this will be one of the major experiments and one of the major industrial uses of space in the future is in the area of pharmaceuticals, and this is just a forerunner of one, and it looks like it's working very well, and we'll have very promising results. So we're glad to have you with us today, and we hope that you will keep following the flight of the Columbia as we go on for the next week. Here comes the studio TV technician down to put in a brief appearance here. Sally?
Is that the vampire that goes with the red blood cells?
Something like that.
In some of the most important tests of the mission, thermal soaks of Columbia, the vehicle was maneuvered into an attitude relative to the sun, which exposed the structure to either extremely hot or extremely cold temperatures. Mission controllers determined the effect of the soaks on the vehicle and its systems by monitoring the readings of temperature-sensitive instrumentation located at various places on the orbiter's structure. They also devised a simple way to display the attitude of Columbia in relation to the sun using a device called the thermodillo, so named because the object representing the orbiter is a popular animal in Texas, the armadillo. The position of the armadillo represented the attitude of the vehicle, and the flag reported its thermal status. The bottom part of the device, called the consumadillo, showed the status of consumables throughout the flight. After maintaining attitude for an extended period of time, the payload bay doors warped temporarily, which was expected because of the extreme temperatures encountered. To measure the exact amount of warpage, the doors were put in the closed position. And the amount of gap, or overlap, was measured by the crew using a theodolite instrument. Then the doors were reopened for the next thermal test. The astronauts reported much less warpage than was predicted by pre-flight engineering studies. Good news to flight planners and commercial users for future shuttle flights. Special measures will not need to be taken to cool down or warm up the doors before they can be closed. Although the astronauts had little appetite and difficulty sleeping their first 2 days in space, they gradually adjusted to the weightless environment. Lousma suffered motion sickness, and Fullerton experienced loss of appetite, a side effect of the motion sickness pill he took pre-flight. The flight surgeon prescribed food and sleep, and mission planners scheduled a less strenuous workload for Flight Day 3 so that the astronauts could recuperate. The first zero-gravity treadmill was used on STS-3. It was designed by astronaut William Thornton to simulate running in an Earth gravity. Since the muscles do not have to work as hard in zero gravity, regular exercise must be maintained. For their welcome home, the crew wanted to look their best. With only one personal hygiene area on board, Jack and Gordon had to take turns. In fact, because of the limited storage space on board, the crew shared almost everything with each other. Back on Earth, winds were beginning to pick up at Northrop Strip. John Young, commander on STS-1, simulated the same approach to runway 23 that the astronauts might be attempting very shortly. Young reported to Mission Control.
There's about 2 miles of visibility on runway 17 and runway 23 is covered up in sand. I think we ought to knock this off, over.
Okay, we got you, John. We copy and concur.
Yeah, I'm sorry, you guys.
Not your fault.
The wind was gusting over 50 knots. And deorbit burn to put Columbia in the correct attitude for entry into Earth's atmosphere was only 40 minutes away.
Columbia, Houston, through Ascension, over.
Hearing you loud and clear, Steve. How many?
Roger, got you 5 by. Jack, we talked to the STA again between Bermuda and Ascension, and as you could probably surmise, the winds have been coming up all day. It was still acceptable until his last pass, but during John's last pass, the visibilities were unacceptable and the turbulence was severe, so it's not a good day, and we're going to wave off for 24 hours, over.
Okay. We've had a good drill.
The good drill showed once again the flexibility of the space transportation system. Flight controllers altered the flight plan just minutes before committing to entry. Columbia had enough fuel and other critical supplies to last at least 24 more hours. In fact, 72 more hours if necessary. Lousma and Fullerton went to bed early that night, fastening themselves to restraints behind their ejection seats, a favorite place to sleep during the mission. Tomorrow, they would attempt to land at Northrop Strip earlier in the day, before the winds began to gust.
Houston, Columbia.
Roger, go ahead, Gordo.
Okay, we're looking straight down at Northrop. It looks a lot better today than it did yesterday.
And it is a lot better there, Gordo.
And what kind of a turn are you betting on for 2-3 at this point, Steve?
Okay, Jack, first of all, you are go for the deorbit burn, and the winds right now are favoring runway 17 with a right turn.
Okay, we're going to select that runway 17, item 4 with right-hand turn.
Okay, that sounds good. Columbia, Houston, through Buckhorn, configure AOS.
Okay, we're reading you loud and clear. We got the PTI so far, and take a look at our ground track and nav, please.
Roger, energy and ground track are good, and nav is great, Jack.
That's good news, Steve. Thank you. This is really a beautiful flying machine.
Columbia, Houston, have an update on winds and weather when you're ready.
Go ahead.
Roger, a high scattered cirrus deck over the field. Surface winds 180 at 11, Altimeter 3003. Over.
Okay, I got them.
Columbia Houston, show you intersecting the hack now, passing 26,000. Looks good. Columbia Houston winds 190 at 14.
Wait where you go.
Columbia Houston, go for auto to interglide slope.
Okay, we're in auto, Houston.
Roger.
Pre-flare, Houston.
Roger.
Gear coming. Gear down. 20. 10, 5, 4, touchdown. Nose gears 10. Nose gears 5, 4, 3, 3. Touchdown. 10 vanilla, amigos.
STS-3 was the most successful mission of the flight test program so far. 4 months before liftoff, the launch date of March 22, 1982 was established. And on that date, Columbia was launched. Mission planners were able to exchange Day 4 for Day 3. And Columbia showed its capacity to remain on orbit longer than planned.
Okay, wheels are staffed, Houston.
Okay, Columbia, welcome home. That was a beautiful job.
The Space Shuttle has brought us closer to something else. After his return from space, Commander Jack Lousma said it best.
I think we rekindled that patriotic spirit that has been lingering in the background, that has wanted to come to the surface. And I think that the Space Shuttle has caused that, in a sense, to happen. And I think the Space Shuttle is great for that reason. The whole transportation system is something that is good about America. People are beginning to realize it and be proud of it.
STS-3 has clearly demonstrated the versatility and flexibility of the space transportation system. It has brought us one step closer to the beginning of a new era, routine operational spaceflight.